Intermediate value theorem. Okay, that's the statement. I won't read it out again, or maybe I will. If a function f is continuous from a to b, including both those points, then somewhere between a and b, the function must hit every number between f at a and f at b. Okay? That's as intuitive as it could possibly be. Okay? If you have to get from here to here and you've got a continuous thing, then you've got to hit every value in between. That's it. Okay? Because continuous functions can't jump. Okay. In particular, if you have f at a and f at b having different signs, so one of them negative, one of them positive, and again f is continuous from a to b, including both those endpoints, then at some point the function has to cross 0. And those are the things we talked about. Does that make sense? You have questions about that? And if you're continuous, you're connected up, you can't jump over anything. Okay? Another way of saying this is that continuous functions can't change their sign from positive to negative or negative to positive without going through a 0. Okay. I wanted to mention this because you like it a lot. I'm bamboozled because the chalk is all non-white. Okay. You guys out here like to do this kind of thing, so I'll bring this up. If you were asked to solve something like this, if you were asked to solve something like that, okay? A lot of you might do this. You might go, okay, what are the zeros of this thing? 2, minus 1, and 3. Maybe some sort of a number line or something similar. What did I say? 2, minus 1, and 3? I meant 2, minus 1, and minus 3. Okay? You do something like that, and then a lot of you, what you do is you just pick some number over here, like minus 4, you plug it in, and then you get the sign of f. You pick some number in here, plug it in, see what the sign is, and then this was f. Okay, and say that's the sign of f, so you get plus, minus, plus, plus. Okay? Plus, minus, plus, plus. Okay, is that a thing people do? That plugging in thing? That is? Okay. Right, so you plug in some random number over here, a convenient number over here, you plug it into this, see what the sign is, and record that. You plug in some random number over here, see what the sign of this is, and record that, and so on. Okay? Okay, now the reason you can do that is because of this. Okay? A continuous function, like a polynomial, is only going to change sign at its zeros. So the reason you can ascribe to this whole open interval whatever sign one number in it had, okay, the only reason you can do that is that this function will only change signs possibly at the zeros. Okay? If IVT weren't the case, or if this guy wasn't continuous, you wouldn't be able to do this trick. Okay? You wouldn't be guaranteed that any point in here would have the same sign as every point in here. Does that make any sense? Okay. Put it this way. The reason your method of picking any point in here, okay, and assigning a sign to the entire region, the only reason that works is because of IVT. Is because you're guaranteed that the function won't change its sign until you hit another 0. Okay. Bottom line, you can do this because of IVT. Now, if someone had told you, solve you know what, if you don't write any of this down, you'll be fine. Okay. You can't do that with this thing. Okay? You can't say, what are the zeros of this? The zeros are -1 and 2. Again, I'll get out of this area in a minute. Okay. The zeros of this guy are -1 and 2. Okay? You can't assign a single sign to this interval, a single sign to this interval, and a single sign to this interval. You can't do what you used to do with this guy. And the reason is this guy's discontinuous, okay? It breaks at -3, okay? So your little method here doesn't work, okay? Because IVT doesn't work for discontinuous functions, okay? So that's a warning. That method only works if you're continuous, okay? So that isn't good enough. You need to include discontinuities. So you need to include that break, okay? I appreciate this won't make sense to some of you, okay? And if it doesn't make sense and you care, let me know. And if you don't care, that's fine. Okay? Bottom line, continuous functions only can change their signs through zeros, and discontinuous functions can also change their signs through points of discontinuity, as well as zeros. Okay. So notice this guy breaks at -3, and this guy also happens to jump across the x-axis at -3. Okay? So if you'd ignored that, you would have missed that. Okay? Discontinuous functions can jump. Okay? Anyone want to ask me? Other than, what the heck were you talking about? Okay. All right. The point of that was to link that to something I know that you do. Now, something else I said I'd mention at some point. All right. Any polynomial of odd degree must have at least one real zero or root. Okay, so if you have a cubic polynomial or a line that doesn't have infinite slope, or a quintic polynomial or anything like that, it's going to have at least one zero. Okay, which is not something you can say of polynomials with even degree. For example, x squared plus 1 has no zeros, okay? This graph looks like this. Yeah, it has no zeros. But if it has odd degree, the polynomial, then you're guaranteed at least one zero. Okay? How could we show something like that? Okay. I'm going to erase this because this is not odd. Okay. For example, something like x to the 5 plus pi x to the 4 plus e x to the 3 minus 1. Okay, this has odd degree. The highest exponent you see is 5, that's odd, it has odd degree. Okay, how can we show this must have at least one zero? If I pick an x that's big enough, okay, this guy's going to be positive, and it's going to be so big that it's going to swamp out all of these guys. Okay? So for big enough x equals a, or for big enough a, fa must be positive. Okay? If I pick a big enough number and stick it in here, we're going to get this guy being positive, and it's going to swamp out the rest of these guys. Okay? So f is going to be positive. That's for big enough positive a. for big enough negative b, what's going to happen? This guy's going to be negative, and it's going to be so negative that it's going to swamp out all the other guys. Okay? So as a result, f is going to be negative. In other words, if you have something of odd degree, okay, if you go far enough that way, let's say it's positive, then if you go far enough that way, it's going to be negative. Okay? Or the other way around if there's a minus sign in front. Okay? If there's a plus sign in front, then again, if you go far enough that way, it's going to be up there. If you go far enough that way, it's going to be down there. Hence, this memory aid. Okay? Does that make sense? Okay. You expect cubics to look like this. You expect quintics to look like this. Okay? Like that. Okay? It goes up that way and down that way. Or if there's a minus sign in front, the other way around. Okay? The point is, because at some point you have to switch from minus to plus, it's got to cross 0. So what does that tell you? It's got to have at least one 0. Okay? That's the point. Okay? Okay. And again, this works because these kinds of things, or any polynomial, is continuous everywhere, and so it's certainly continuous between A and B. Or in other words, for something connected up to get from down there to up there, it's got to cross 0 at some point. That's it. Okay. Now for the stuff you care about hearing. Incidentally, I have another picture. Even degree polynomials do that. Okay. Good? Yep.
So, is like FA like referring to the coefficient?
If you evaluate that function at a big enough positive number,
Okay.
then the result is going to be positive.
Okay. Like, can you like draw us an example?
Literally that. Okay? Flip him around. Here, I'll draw you an example. Okay? If you go far enough to the right, this has got to be up here. If you go far enough to the left,
Oh.
you've got to be down here. So at some point, you've got to cross.
Oh, okay,
So it's got to have a 0.
Okay, yeah.
That's it.
Okay.
Okay. Okay. That's just an example of how you can use IVT. Okay, so now I'm going to show you how to find roots again. And what's going to happen is you're going to give me a random polynomial, and I'm going to find a solution of it. Okay? You're going to give me a random cubic, because I know that a cubic is going to have a solution, and I know that if I go far enough that way and far enough that way, I'm going to get opposite signs. So that's what I'm going to do. So y'all are going to give me a cubic. So the tester becomes the tested. Okay. I will find an approximate solution of f at x equals 0, where f at x equals what? Okay, give me a random number.
5.
Thank you. 5x cubed. Another one?
7.
Right, I'll do 2 and then 7. Pick some minus ones. Pick some irrational stuff. You know, the minus root 2 plus 7 pi. Okay, one more. Hello?
-13.
Thank you. Excellent. Okay, there we go.
Oh.
What happened? Okay. All right, that's a cubic again. This whole thing, okay, the point of this was to show you that cubics do this kind of thing, and so at some point there's got to be a 0, so I'm not wasting my time. Okay, here we go. I'm going to do the bisection algorithm. Here we go. I realize this is grittier than usual. All right. So let's see if I can get a 0 between minus 10 and 10. You don't have to know what I'm doing here. 5 minus square root 2, 7 pi. 5 minus square root 2, 7 pi, and minus 13. Okay, so at minus 10, it's that god-awful number. And at plus 10, it's that number. Hey, look, if I go far enough, you get big numbers that are positive and negative. Okay. Excellent. All right, so here we go. Okay, I'm going to do this. Please follow along. I'm going to do this partly with pictures, okay? So please try to understand what I'm doing. Here we go. So, what I've done is this. I punch into my calculator minus 10 instead of x here, okay? So I plug minus 10 into this thing, I evaluate it, okay? And I get that negative number, okay? So I know that minus 10, the function is downstairs. I plug 10 into this thing, okay? I get that large positive number. So I know that at plus 10, okay, this guy is upstairs, okay? Above the x-axis. Does that make sense? Okay, this guy's continuous, yeah? You have to check that every time, right? And this is a polynomial. Yes, it's continuous, and it's certainly continuous from here to here. In fact, it's continuous everywhere, so you're okay. So you can use IVT, bisection algorithm, and so on. Okay? IVT tells you that to get from down here to up here, for a continuous function, you've got to cross at least once. Okay? And it's my job to try to narrow down where that is. Okay. So somewhere there's at least one solution. So, it's bisection, so we bisect. The midpoint of minus 10 and 10 is 0. Okay? So now I evaluate this function at 0, and I'll get minus 13. So I'll be down here. Okay? All right. And I'll try to keep track over here. The left point, the middle point, and the right point at each iteration. So minus 10, 0, and plus 10. Okay. Is it this interval or this interval that's guaranteed to have a 0? 1 or 2? 2, thank you. Okay, good. Okay, there could be stuff here. We don't know. Okay, but IVT tells you there's definitely something here. Okay, because you go from minus to plus. Excellent. So those are the guys. So now I take that and I bisect that. Okay? All right. So now I evaluate this thing at 5. And I get a positive number. Okay, so I'm up here somewhere. Okay? So again, we don't care about this guy anymore. All right, these guys are the same sign, so we're not guaranteed anything there. We're not guaranteed a 0 there. These guys are opposite signs, it's got to cross somewhere. Okay? So we've narrowed down to between 0 and 5. I've got to have a solution between 0 and 5. Okay, so now we have 0 plus 5. Plus 10. And I'm saying we're guaranteed a 0 between 0 and 5. I'm writing that table because, I don't know, if you program this, that would go in the computer, because I suspect in the assignment you're being asked to provide something like this. That's why that's there, okay? In my head, I'm thinking of this picture. Okay?
Like, how did you get the positive 10? Like, to circle?
I knew that if I go far enough this way and far enough that way, I'm going to get different signs.
Yeah.
Because of the Travolta and that picture.
But, like, why did we circle, like, 0 and
Okay, 0 is downstairs, 10 is upstairs. So here is the interval where I definitely have a 0.
Okay, like, what, how...
So in my next iteration, I use them.
How do we know that there's a 0 there?
Because you go from downstairs to upstairs.
Imagine it like a graph.
Okay.
Thank you. No? Yeah.
So you were just subbing values into those.
For the plus 10 and minus 10?
Yeah.
Look, the plus 10 and minus 10, I knew that if I go far enough, I'll be okay. Okay? Because of all this stuff.
Like 5, for example.
Yes, I bisect this. Okay, so I started with this, and then I bisect, and then I evaluate. Okay, bisect means find the midpoint. Yeah, does that make sense? And then I do the same thing here.
Yeah.
Okay. All right, so again, right, what did I do? I bisected, then I found that there's got to be a solution here. Okay, here. So now in the next iteration, those are my endpoints. Then I bisect that. Okay? Now I found this is downstairs, this is upstairs, so we've got to cross somewhere in here. Okay? So now I know that my solution is in here somewhere. Okay? So now these are my endpoints. Okay? I know there's got to be a solution here. All you're doing is you're narrowing down by bisecting and looking for where the sign changes. That's it. But I recognize you have to practice this. Okay. I bisect this. I get 2.5. I evaluate the function at 2.5. I get a positive number. Okay, again, I pick where the 0 should be, I make those the new endpoints, and then I bisect. I find where the 0 should be, I make those the new endpoints, and then I bisect, and so on and so on and so on. Okay, again, these are both positive, so we're not guaranteed a crossing. These are of opposite signs, we're guaranteed a crossing here. Okay, those become the new endpoints. We will stop at some point here. Okay, now I bisect again, 1.25. I value the function there. Positive again. Oh boy, positive again. Okay, nothing guaranteed there. There's a sign switch there. So I know my 0 is between 0 and plus 1.25. Okay, I'll do one more because I'm running out of real estate. What is that? 0.625. Okay, I bisect. I get that positive answer. The sign changes from 0 to 0.625. There you go. So there's got to be a 0 there. And there I'll stop, okay? Because it's getting ridiculous. Okay? What's that? Oh, bet, yeah.
What if there's more than 1 0 and we miss a 0?
Well, I've only said I'm going to find 1 0.
Okay.
Yeah, I never said I'd find all of them. In fact, there may just be 1, there may be 3, there may be 2. Yeah. Yeah, this finds a 0. It's guaranteed to find a 0. Yeah.
And we're stopping there because it's close just to.
I'm stopping because y'all are going to, torch me if I keep going. Right? I can't spend the full hour
Yeah.
doing this. Yeah. Why you would stop is if you've reached the precision you need to get to.
Yeah.
Yeah, in a problem. I'm stopping because it's getting ridiculous.
Yeah, because like
Yeah.
if like you had like -10 and like 2, I don't know, like like if it was never mind.
Okay.
Like never mind. I kind of get it now. Thank you.
Does this make any sense? Yeah, go ahead. To find zeros, yes. To do this, no. Right? You need to do this thing. You need to do this thing where you set up 2 endpoints, okay? Probably we'll give them to you, okay? You set up the endpoints, and then you bisect. And you evaluate the function at those 3 points, okay? You evaluate the function at those 3 points, and you see where a sign switch happens, okay? The only guess I did was this. The first thing I did was a guess. That's it. Everything else was completely determined, right? You can make a computer do this, okay? You can tell the computer, okay, I'll give you these things. You cut it in half and evaluate the function. Find where a sign switch happens. That tells you where your new interval is. Then bisect. Evaluate, see where a sign switch happens. And then keep going. That's it, okay? So all you do is you bisect and evaluate over and over and over again. Okay? And each time you pick where your new interval is, and it keeps getting narrowed down. Okay, yeah?
In this case, we will never really get to it because.
You might happen to get to it, but probably not. No, it's gonna be irrational and ugly. So no, you won't get to it exactly. But you'll keep narrowing down, you can get as close as you want.
But on movie, it's like we have to do this like 3 times.
They'll say you have to do it 3 times. Okay, you guys have any questions about this? Because I know people are confused about this, and I don't know if this has fixed anything.
Perfect. For me.
Questions? No? Okay. Draw yourself a picture, okay? Again, you're going to be putting this into Mobius, but draw yourself a picture, okay? You know what you're looking for. And if you have any questions, I'll answer them. Okay. And here, let's see what the actual answer is. My feeling's gonna be so steep that it won't be interesting. Did that even work?
You forgot a square on the X.
Thank you. Hey, look at that. Okay, crosses at 0.57, which is between there.
Oh,
Good. If I'd have been wrong, it would have been very embarrassing. Okay? Questions?
how would we know that though?
How would you know what?
Without like graphing it? Because
Well, you wouldn't. You do this to find it. That's the whole point.
But it didn't change signs.
What's that?
It didn't change signs.
Say it one more time.
It didn't change signs.
Between where and where?
0 into 0. I mean, 0.
It does change between 0 and 0.625. It changes between 0 and 0.625, which is where I said your answer must be.
Oh, okay.
Where is the graph?
Okay, right.
On negative number. Like you can't.
Look, again, I know this is hairy. If you've got questions, ask me, okay?
Plug it in.
Otherwise, I'll just keep doing things my way, and who knows if you understand them. Okay, one fun, silly thing, quickly. In class, we tried to solve cos x equals x this way. I wanted to show you that there's a very, very idiotic other way of trying to solve that kind of thing, which I think is funny. It's called fixed point iteration. You don't have to know this. This will take about a minute. Fixed point iteration. Okay, and I'm trying to approximately solve cos x equals x. Okay? This method works for some things like this, okay? For some things where you have x equals some function of x. Okay? So real quick, we're going to try this. Okay, gang, give me any number.
46.
Thank you. 46. All right. Again, this is an alternative for solving this particular equation, which I think is hilarious. Okay, there we go. So what we do is we take the cos of that guess, okay? And for this equation, any guess works, okay? So I take the cos of what you said, okay? And I get that, okay? Then I just take the cos of that. Then I take the cos of that, and I keep doing that. You'll notice that that first digit has now settled down. Now the second digit is settling down. Now the third digit's settling down. So all you do is you put the number in your calculator and you keep punching cos. And look at that. If I keep doing it, eventually look at what I got. A solution to 6 decimal places. And all I did was put some random number into my calculator and keep punching cos. Okay? So that's a stupid way of finding a solution to some equations. So all you do is you pick a number, any number, then keep taking cosine. Yeah.
What does that do then?
What is that?
What does that do number? What does that represent?
That's the solution. Look at that. Cos x equals x. We wanted a number that does that. Cos that equals itself. So we've solved it in the dumbest way possible. Does that make sense? Right? So by math magic, which I'm too dumb to understand, okay? Some functions can be solved like this, okay? Yeah, it's called fixed point iteration. You're looking for a fixed point of this thing, which is a solution to this, okay? Look at that, it clearly looks like that, and we found an answer. Does that make sense? Okay? You don't have to know this. It's just a silly other way of finding a zero. Or a solution. Okay, I talked about this temperature example for intermediate value theorem. If you want, guys, I'll talk to you about that next week, or this week if you really want me to, but I can do chain rule otherwise. Okay. Questions? Okay. If you have questions about this, let me know. All right. Okay, so to conclude this thing, I'd say x is approximately equal to 0.739085. All right, chain rule. All right. Find me the derivative of the square root of x cubed plus x squared plus x plus 1. That's the thing I was talking about. That's the thing I brought up in lecture. I can prove that if you want, okay? So if you want me to prove that, say something. Otherwise, I'll do chain rule. I can do that next week when you probably also don't want me to. Okay. All right. All right, find me the derivative of this. So what I would do first is rewrite it, possibly. Like that. Okay? And I'm going to do all the steps explicitly so everything's clear, and then as we go on, I'll be more and more in my head. Okay. So this thing is a composition. F at g at x. Okay? What's the outer function?
X square root.
Thank you. Excellent. Okay? You can write square root, you can write u to the 1/2. Okay, and g at x, the inner function, is all this, yeah? Okay, so the outer function is this thing, or the square root, and the inner function is this bit. X cubed plus x squared plus x plus 1. Okay? Okay. The derivative of this. By the power rule, the 1/2 comes down, and upstairs it gets reduced by 1. So you got 1/2 u to the minus 1/2. Okay, or if you remember, the derivative of square root x is 1 over 2 square root x. The derivative of g is what by the power rule? 3x squared plus 2x plus 1. Yeah? Again, f is the outer function, g is the inner function. And then we just do what we're told to do. Derivative of outer evaluated at inner times derivative of inner. Okay, f prime is just this thing. That's okay? Evaluate every function and every derivative at what they see. And just plug in. Very dumbly. And that's it. Yep. If you want to rewrite this, and I don't know how low you can see. Or if you want to rewrite this, if you want to rewrite this, 3x squared plus 2x plus 1 over 2 square root x cubed plus x squared plus x plus 1, if you feel like it. Yeah? That's it. You spot the inner function, you spot the outer function, you do what you're supposed to do, and you'll be good. Good? Okay. Okay, I'll do another example, and I'll do it using version 2, so that you get to see that.
So you have to know how to do the other way?
No, you can do whatever you like. Whatever you like. And odds are you won't be spelling this out every time. If you get used to this, whoever asked that, you'll just in your head, right? Who asked me this? You asked me this? Thanks. I like how you look inconspicuous as soon as I look at you. Okay, you want the derivative, that's not a minus sign, of cos x plus sine x. I may stumble on stuff that's in your assignment, so, hey, forgive me. Okay. So again, we have a composition. So again, we need chain rule. That's a 3 up there. So let's try to use this version. Okay, what's the outer function? The cube root. What's the inner function? This thing. Yeah? And that's it, same deal, differentiate, except using the other notation. Okay, the derivative of this guy, you bring the 1/3 down, and upstairs you reduce it by 1. So you get 1/3 u minus 2/3. The derivative of this guy, with respect to x, the derivative of cos is minus sine. The derivative of sine is cos. There you go. Now you just plug in. dy over du, dy over dx, sorry. dy over dx is equal to dy over du times du over dx. And you just plug in. Okay, now I'd be upset if you wrote that on a test because what? You've put some variable I know nothing about in here, okay? So you've got to finish with everything in terms of the original variables, okay? You can't have just stuff floating around. So what was u? It was this. So you've got to plug that into here. And that's it. Okay? Does that make sense? All right. And by the way, until you tell me, I have no idea what you guys have trouble with and what you don't. Okay. So now, excitingly, I'll do something I would have done in lecture. Any questions?
Are we allowed to go over,
Are you allowed to do what now?
go over chain rule, questions from assignment right now, or no?
Tell me later.
Okay.
Yeah, tell me later so I can get through some of this. And because I know you don't like to talk to me, again, if the IDT stuff was confusing, let me know. Anytime. Okay, let's do this thing. This would have been in lecture. What do I find? Again, determine the derivative of cube root 1 sine x. Okay. Okay. What I'm going to do is I'm going to rewrite this as usual. So I can use familiar rules like that. Okay? What's weird here? 1 function, 2 function, 3 function. We got a composition of 3 functions. Yeah? So not 2 links, but 3. Okay? So what do? We apply chain rule twice. All right. What's the outer function here? The cube root. Good? Excellent. Okay. So, on my first application, the outer function is, use the 1/3, whose derivative this. I suspect we just saw. Yeah, good. Okay, and the inner function is this. Does that make sense? Okay, spot the outer function, spot the inner function. Okay? So, derivative of outer function evaluated at inner function. Multiplied by derivative of inner function. Sine x. Okay? Derivative of outer function evaluated at inner function times derivative of inner function. Okay? And now what do? That's a composition as well, so we have to go again. Okay, on our second chain application, the outer function is ln, whose derivative is 1 over u. Okay. Take the derivative and get 1 over u. And the inner function is sine x. Okay. Derivative of outer, the reciprocal function, evaluated at inner, which is sine x, times derivative of inner function. That make sense? So I just go from the outside in. And derivative of sine is just cos. So now I'm done. One, two. Derivative of sine is cos, so I've got cos x over sine x. Okay? And if you want to rewrite that in a way that, say, Wolfram alpha would be happy with, cos over sine is cotangent. Good? You work your way from the outside in and apply chain rule as often as you need to. Okay. The colors are weak here, but what do we got? F is meant to be black. F is these spires. And F prime is the sort of more, how do I put this? The other one. Okay, do all the checks you usually do, okay? Make sure that the sign of f prime makes sense given the slope of the tangent at f, at a point of f. And what feature do we have here? Cusp. So, yeah, good, cusp. Okay, the derivative fails to exist there in that special way. Okay, so we have cusps there, and so on. Okay, so function's not differentiable there, and it's certainly not differentiable where it's not defined. That's just for the sake of giving you a picture. Okay? All right. Okay, I'll post all of this in case you're, or it's already posted, I think, under lectures. Okay, this is what we did in general terms. Okay, so if you've got three links, so a composition of three functions, this is what you do. Literally, this is what we just did. We want the derivative of the whole composition. So derivative of outside times what it sees, derivative of outside evaluated at what it sees times derivative of inside, okay? And on the first go, this is the inside function. Then, to get this guy, to get its derivative, derivative of outside function, evaluated at what it sees, I can't talk here, evaluated at what it sees times the derivative of the innermost function, okay? So work your way in. So you could do that And in general, you get that result. So if you like writing down that result, you can do that. Okay, and just use that every time. Okay? And then if you have a composition of 4 functions, you again either apply chain rule over and over again sequentially, or you remember or build the 4 function version of this. Okay? And this is why it's called the chain rule. We're making a chain. Okay? And there's the Leibniz version of that, which is as beautiful as the first one was. Because if you thought of these as quotients, cancel, 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 dy over dx. Okay? It looks good. You should be able to remember that second one. Okay? And the first one makes sense too. You just work your way from the outside in, keep taking derivatives, and always evaluate at what that function sees. Okay? And again, if you don't feel like doing this, you just keep applying chain rule in sequence like that. Question? All right. We're okay? Okay. What now? Hey, it's ugly, but we'll do it. Here's a belated question. Can you all see the board and the writing thereon? Yeah? Thank you. All right. Excellent. Let's do this stupid example. Yes. Okay. Differentiate. Where are we now? Square root of 2x over e to the sine x. All right, what rule comes to mind first? Quotient. And I did that too, but you could be smarter than that, and you could do... So I did quotient, okay? And you can totally do quotient. What you could also do is you could rewrite this thing. Anyone? Yeah?
Can't you rewrite it like a product?
Yeah, you could, exactly. There we go. Good. Yeah, so you can do that. And if you don't like quotient rule, you can just use product and chain rule, and that always works. Okay? So whenever you have a quotient, you can rewrite it as a product. Okay? And using the chain rule and the product rule, you can evaluate the derivative that way. Okay? If you don't like quotient rule. And in fact, you could prove the quotient rule this way. All right, here we go. Hey, quotient or product? Who wants quotient? Somebody vote for something. Who wants... Whoa, yeah, quotient. Product. Ooh, yeah, okay. Whoever wants quotients, I'll show you whenever you want. Okay, here we go. Product rule. So, I'll do this explicitly. Derivative of first times second plus first times derivative of second. You can do as much of this in your head as you feel comfortable doing, okay? But until you're sure, write everything out. Okay. This bit we can do in our heads, yeah? Okay. The outer function is the square root function. Okay? Its derivative is 1 over 2 root. So, we have 1 over 2 root evaluated at the inner function, which is 2x, multiplied by the derivative of the inner function, which is 2. If this is confusing, do that stuff. Do one of the more basic versions, okay? Do version 1 or version 2 that we talked about a few slides ago. Okay. The outer function is the natural exponential. Its derivative is itself. Evaluate that at the inner function, which is minus sine x. Multiply by the derivative of the inner function, The derivative of minus sine x is minus cos x. Minus cos x. Okay, do some canceling. All right. You're pretty much done. If you want to factor something out, you can do that. And there's a few ways of rewriting this as well. Okay, e to the minus sine x, 1 over root 2x, minus root 2x cos x. Okay? And if you want the quotient rule version, I'll do that whenever you ask me.
So essentially, any like e, regardless if it's not x, it's still like the derivative is still the same,
Times the derivative of the top
right?
by chain. Yeah.
So like e of m, it's still got the derivative of that is still gonna be e of m. If that made any sense.
So like e x squared, the derivative with respect to x is e to the x squared times 2x.
No, like I meant like, you know how e of x is like, the derivative is still like,
Yeah.
what happens?
Oh, it's n? Yeah, it doesn't matter.
M or like n or whatever.
They don't matter.
Okay,
A cat, a picture of a cat, it doesn't matter.
okay,
Yeah. E to the cat, differentiate with respect to cat, you get e to the cat.
okay.
Okay. All right. Good? All right. It's been suggested to me that we do this. So let's do this. If you spot a mistake, tell me. If anything's unclear, tell me. If you need another version, tell me. All right. Okay, there's things called hyperbolic trig functions. Who's heard of these things? Cosh and Cinch and these kinds of things. Okay? Full disclosure, I've been to a lot of school and I didn't use them. Much, if at all. But in some applications, they're very useful. Let's spell this right. S-I-N-H, hyperbolic sine, is defined thusly. E to the x minus e to the minus x over 2. That's hyperbolic sine, and hyperbolic cosine is defined like this. Okay?
Do we need to know that?
You don't need to know this, all right? This is for fun, I don't know. This is to introduce you to a wide array of things. In case you're wondering why is it called hyperbolic. Okay, we talked about the unit circle, okay? Let me get this right. Okay. When we trace out an area, a sector of area 1/2 t, that point has coordinates cos t sine t. Okay? You can check that that's what happens when you sweep out an angle t radians. Okay, so that's what happens on a circle. On a hyperbola, this is x squared plus y squared equals 1. This is x squared minus y squared equals 1. On a hyperbola, if I sweep out an area, you're very safe not writing this down, okay? If you sweep out an area of 1/2 t, guess what that's going to have coordinates of? Cosh t, sinh t. So that's why it's called hyperbolic. Okay. So that's why it's called that, and in case you're wondering where this can be used, one place where it can be used is if you have a heavy flexible cable hanging between 2 points of the same height. that shape is called a catenary, I think. And if you want to describe that curve, you use cosh. It has applications, and there's a lot of applications I know nothing about. All right. Let's take the derivative of something. Take the derivative of sinh. Okay? So take the derivative of sinh. Okay? What is that? By the constant multiple rule, the 1/2 pops out. Okay? Derivative of that is e to the x. What's the derivative of this guy? What's e to the minus x's derivative? Good, excellent. Okay, so use chain rule. Minus e to the minus x. So you get e to the x minus e to the minus x. E to the x plus, look! Look everyone.
Same as cos.
What beautiful magic, right? If you know about complex numbers, and maybe I'll say this to you at some point, this is reminiscent of something with complex numbers, okay? If you don't know, maybe you'll hear it from me someday. Okay. All right, the derivative of sinh is cosh. What do you think the derivative of cosh is? Yeah, but no. Just sinh. But thank you, I love that, that's good. Here we go, derivative of... And you can show that if you want in the same kind of book. So with these guys, no minus signs. Okay? So you can try that and confirm that for yourself. Okay, let's do an identity. Let's do this one. Prove to me sinh 2x is equal to, hey, guess what? 2 sinh x cosh x, which is familiar. Okay? So yeah, some of this stuff looks really familiar, some of the stuff not so much. Okay, left-hand side. Just plug in. Okay, just plug into that. E to the 2x minus e to the minus 2x over 2. Yeah? And the right-hand side, all right, what happens? 2 divided by 2 divided by 2 is 1/2. Okay, what's left is going to be a difference of squares, right? A minus b times a plus b. So it's this guy squared, and ex squared is just e to the 2x, minus this guy squared, e to the minus 2x. Okay? And you may note how much easier that is than trying to prove the equivalent trig identities. But if you know about complex numbers, that becomes easy too. Okay? All right, so that's one identity. If you feel like fun at home, you can prove these ones. Cosh squared h minus sinh squared. I'm saying h instead of x, aren't I? Cosh squared x minus sinh squared x is equal to 1. So it's the hyperbolic version of the Pythagorean identity. And you can prove this one if you want. Cosh 2x is equal to sinh squared x plus cosh squared x. Okay? So like screwed up versions of the trig stuff. All right? Okay, one more thing, I'll do a sketch. All right, so someone told you to sketch these two functions in a reasonably sloppy way. You could do this. Okay, so sinh is 1/2 of e to the x minus 1/2 of e to the minus x. All right. I may need more colors. Here we go. That's 1/2. Okay, that's 1/2 e to the x. Okay, it goes through there, and it's growing. Okay, what does minus 1/2 e to the minus x look like? 1/2 e to the x looks like that. That tells you flip horizontally. That tells you flip vertically. Flip, flip. Minus 1/2 e to the minus x. Okay? And you can add these puppies. There, you add them and you get 0. As you go this way, this guy dies away, and so you look more and more like this guy. As you go this way, this guy dies away, and you look more and more like this guy. Okay? And you can convince yourself however you want that this is an odd function. Okay, what did I do? Sinh is equal to 1/2 e to the x minus 1/2 e to the minus x. So I can just add those guys graphically. Okay? So at every point, I add this value to this value to get the value of the orange guy. For cosh, what do we have? One half e to the x plus 1/2 e to the minus x. That's 1/2. One half e to the x, 1/2 e to the minus x. Okay, I add those two guys and I get 1. As I go this way, this guy dies away and I look more and more like this guy. As I go this way, this guy dies away and I look more and more like this guy. It's an even function. And remember, cosh x. Each is the other's derivative. Okay? So check the things you expect of derivatives and make sure they make sense with the sketches. Okay? Questions? Again, the only relevance that had to what we've been talking about lately, is we use chain rule, just barely, very briefly. Okay, I'll do one more thing. Okay? Ta-da! Can you see yellow at the back? I mean orange, whatever this is. Can you see that at the back? Okay. Okay, there we go. All right, damped oscillator. for the record, on Wednesday in class, I'm going to just throw up the three-way chain rule slides, just so we've seen them there too. I will do one more example, and I'll talk about exponentials, and that'll be it for chain rule. Okay, damped oscillator. Suppose you have this position function. That is that, yeah? Good. Okay, so suppose you've got something going boing boing inside a viscous liquid, okay, or something else that has some sort of resistive force, and so you don't just bounce forever, you get damped out. Okay, so suppose that's the position in centimeters. Suppose that's time in seconds. And suppose I ask you to find the velocity at time 0.75 seconds. What do you do? Yeah, take the derivative and evaluate it there. Don't you dare do this. Don't you dare plug 0.75 in here, evaluate that, get a number, and then take the derivative of that and say it's 0. Don't do that, okay? It is possible to think that you just plug that into here, get a number, take the derivative, and you'll get 0. And you'll always get 0. That's clearly not how this works, okay? You take the derivative of this thing, and then you plug in. Hey, another kind of notation just for fun. Okay, let's take the derivative. What's the derivative of 1? Excellent, okay. So all we have to do is take the derivative of that guy. E to the minus 2t cos 4 pi t minus 1/3. And again, make sure this makes sense. This function I gave you makes sense, right? You're going bouncy bounce, but your envelope is shrinking down. Okay? And I put in these shifts just to make things more difficult or annoying. Okay? All right, take the derivative. Product rule. Derivative of this, using the chain rule, is minus 2 e to the minus 2t times this guy. Okay, plus this guy times the derivative of this guy. Chain rule again. The derivative of cos is minus sine. So minus sine evaluated at what it sees. Times the derivative of this inner function. What's the derivative of this with respect to t? 4 pi? Again, for both of these, we needed a chain rule, right? Chain rule gave us this thing, and chain rule gave us this thing. Okay? Derivative of cos was minus sine. We evaluated the inside, then we took the derivative of the inside with respect to t. Okay? Yeah, you can expand it out if it makes you feel better, but you don't have to. Does that make sense? The derivative of this is 4 pi. Okay. Almost there. All you can do at this point is make this look a bit cuter. So minus 10 e to the minus 2t. Minus 10 e to the minus 2t. Oh boy. Cos 4 pi t minus 1/3 plus 2 pi sine the same thing. Okay? Again, what do we use? Product rule, chain rule. And that's virtually it. Okay, so we have this guy now, and all we have to do is plug in 0.75. Fun fact, you could rewrite this thing as a single sinusoid. There's addition formulas, there's addition identities that let you write a sum of two sinusoids that have the same frequency. You can write them as one. Okay, but we won't do that. You plug 0.75 into this thing, and here's your exact answer. Okay, the numbers work out. They're those nice signs you know about. Minus 10 e to the minus 1.5, 1/2 minus pi root 3. And that's in centimeters per second. Okay, understand units, okay? This is position in centimeters, that's time in seconds. The velocity better be in centimeters per second. And that's approximately 11.03 centimeters per second. Okay, make sure you can plug in. And there you go. That's the slope of that line I've drawn at the point we care about. Okay? Okay. All right. If you want other chain rule examples, let me know. If IVT is confusing, let me know. Please, please, please let me know. And I will explain it however you understand things. One thing I said was, we talked about compositions of continuous functions, and we said if you have a bunch of functions that are continuous on their domains, and you combine them, either add them, divide them, take the product, whatever, or compose them, then you get another function that's continuous on its domain. And then the question came up, what if something's discontinuous? Okay, and the answer is things get trickier. Okay, so if I feel it's helpful, I'll try to do an example like that next time. Okay, but rest assured things get hairy. And I will take one more minute for those who care to hear this, of just how hairy this can get. I told you about a function once that was defined everywhere, discontinuous everywhere. Okay? That Dirichlet thing. Okay? It's a function that tells you if you're rational or not. Okay? You give it a value, and it spits out 1 if you give it a rational thing, and it spits out 0 if you give it an irrational thing. This thing happens to be discontinuous everywhere, okay? But if you compose this thing with itself, you get a function that's continuous everywhere, okay? Why? Any number I give it. Suppose I give it a rational number. I get 1. If I feed that back in, 1 is rational, so I get 1. If I feed an irrational number in, I get 0. If I feed 0 back in, 0 is rational, so I get 1 again. Okay? So no matter what I put into this mad crazy thing, okay, let's call that f. F at x is 1 for all x, which is pretty damn continuous. Okay? I'm just saying this to make a point, you don't have to know any of this. This is wildly discontinuous. But you can compose it with itself and get something that couldn't be any more continuous. Okay? Okay? This is part of the reason why I'm not too comfortable telling you about this. Okay? So if it's productive, I promise I'll help you next week with that. Otherwise, that's it. Thank you, everybody. Have a lovely night. If you have any questions, come talk to me.